Hello everyone. Today with me I have Jeff Tantsura again. He's like my co-host now, and we have a special guest, Dino Farinacci, with us. We will talk about LISP, Locator and Identity Separation Protocol. It's not new. We have an RFC for that one as well, 6830. And in fact, I think 8-9 years ago, even myself, I deployed it in production network. There are many use cases for it. He will introduce us. This is question and answer type of discussion, but in the beginning, Dino will show us some important things. And please, let's start with Jeff, and after that, we will give the microphone to Dino, and he will continue after that. Jeff, can you please introduce yourself for the new audience?
Hey guys, glad to be here again. Jeff Tantsura, probably you already know by now, at Abstract, heading networking strategy, doing a lot of work in ATF, chairing Crouching working group, chairing Chris working group, and happy to have Dina, who is one of the people who, he built the internet, and besides LISP, if you have work in multicast, it's probably Dina's fault. So Dina, please go ahead. Again, one of the legendary figures on internet and one of the people who was like what internet engineers should be.
Yes, and actually also many people know you from your LISP work, but you did a lot of things. Can you please explain what have you been doing for internet, like Jeff said?
Sure. Hi, everyone. My name's Dino. I'm pretty much a software engineer by training and a network architect as the years went on. I started with Cisco in the early 90s, but before that I was at 3Com and we were building small routers. But basically I started in the routing protocol group in the early 90s when Cisco was a itty-bitty startup. And basically worked on IGRP and IP routing, and we evolved it to IGRP for the OSI protocols. And then I started working on extended IGRP. If any of you have experience with eIGRP, I worked on that. And so I pretty much worked on systems. We built systems, software releases and routing systems, architectural-based system-wide systems during those years of the 90s. And then I worked on the really early versions of IPv6. And then, of course, I did the multicast throughout the 90s to the late 90s. I left Cisco in the late 90s and went to Procket, where we built a high-end router, a half-rack 480 gig router with a complete new operating system. Everything was new in that system. We didn't use any off-the-shelf parts other than an x86 processor, but all the memory controllers and NIC cards and everything were stuff that we built. We built 6 chips from scratch by getting guys from Sun Microsystems that built a lot of the Spark systems to build that router. It was a great fun project. 5 years later, Cisco bought that company called Procket, and we then moved to software engineers. We split them up between iOS XR and what became NXOS, and a lot of the Procket OS code was our code from Procket that it went into NXOS. That's now the data center products at Cisco. I left Cisco then, so that was in 2004. In 2012, I left Cisco because I wanted to make LISP be something that was more industry-wide rather than Cisco-wide. We did a lot of the work starting in 2006 with LISP in the IETF and the IRTF. First, really from 2006 to about 2009, we were doing most of LISP in the IRTF, and then we made a working group in 2009 and been doing it ever since. I worked on LISP then from Procket until I left. We worked on NXOS and data center products, and then I introduced LISP, and we ran it on all 3 operating systems on probably a dozen platforms. Cisco has a pretty huge array of Cisco products, or of LISP products right now, even on the newer generation platforms. So that's been pretty successful from a product launch, but we didn't get broad adoption from all the different vendors. Before I get into things, I'll just say in 2012, I left Cisco to start Lispers.net, which was just my own consulting company. And rather than being a vendor, which was really cool, I'm now a partner with people that I work with. And so I help them deploy their networks. I help NBC Sports with the Olympics. I've been to the last 3 Olympics and helped them design the network. If you go to lispers.net and scroll to the bottom, you'll see all the different types of companies I've worked with since 2012. I still participate in the IETF. I've been, last spring was 30 years that I was in the IETF. So I've written a lot of internet drafts and RFCs and have a lot of patents on internet routing, protocols, software engineering, those sorts of things. I'm still quite a bit of a coder. Lispers.net is a consulting company that also has a product. We don't sell the product. It's an open source project that allows any of you to play with it, just to understand the protocol and what sort of things it could do. Now, Lispers.net, the implementation, is a very feature-rich implementation that can do a lot of things that this basic protocol that I'll introduce to you can do. We will go above and beyond what it could actually do, and you'd be quite surprised. Some of the use cases right now are like IoT and blockchain, things like that are interesting projects that we're working on. Space networking. These are, because we have this level of indirection and routing, we can do all kinds of cool things. I'll pause. Go ahead.
Let's move on. What we have on the screen, by the way, let's explain.
Okay, so basically, if you just understand this slide, all the use cases stem from this slide because Lisp is pretty straightforward. One of the questions is what's the difference between the data plane and the control plane? We'll answer that by just looking at this slide. So what we decided to do with Lisp is the acronym Locator ID Separation Protocol is really what we did. There's this semantic with an IP address today that means both location and identity. So when I want to talk to Jeff, I just told you I want to talk to Jeff. That's an ID of a person, right? But when I send a packet to Jeff's IP address, I'm not sending it really to him. I'm sending to where he is attached on the internet, right? If he's attached on his Wi-Fi network, I'm really sending it to a customer at Comcast, perhaps, and not to Jeff. I know I'm talking to Jeff at the application layer and at the transport layer, but I really don't know if he's going to change. And if he walks into a Starbucks, I still want to talk to Jeff, but his location changed, so now the IP address has to change. So what we want to do is we want to take the identity and location semantics out of the single IP address. And so when I want to talk to Jeff, in the Lisp world, it's called an endpoint ID or an EID. It's just a regular IP address, but the routing system doesn't know about it. The routing system just maps that into where his current location is. So if you look at this slide here, at the bottom you see there's a host A that wants to talk to host B. That could be 2 cell phones. That could be a computer talking to a service. It could be an IoT device. Whatever you can IP address something, any entity, you would give it an EID. So what happens is, the first thing is when host B comes on the network, it's sitting at a particular spot topologically in the network. And the only way to get access to it is it has a locator called Y. And it turns out here, Y is the IP address, a routable IP address of this router node that's in the network. Y could be co-located with B, Y could be a hypervisor, and B could be a VM, B can be a container, Y can be the Ethernet interface of that system, Y could be deeper in the core, it could be put anywhere. But the whole point is if you want to send packets to B, they have to be encapsulated to Y. So we use encapsulation, an extra header that's put on. So the idea here is if host A sends a packet, that packet at time number 1 is a packet with a source address of A and a destination address of B. When that packet arrives at this default exit router X, it will then put another header in front of that AB packet saying that it's the source X and the destination is Y. So X and Y are locators. So we always refer to EIDs and locators as the split in locator ID separation protocol. So when X emits the packet into that core network, that is Y and X are routable IP addresses, and the core network knows about it. BGP has a prefix that matches Y, and all the BGP routers that are along that arrow by 5 are actually moving the packet to Y. If host B had a connection to Y and Y prime, two different routers, or the same router with two different interfaces to either the same or different ISPs, so be it. The BGP routing system would deliver the packet to Y or Y prime. When Y gets the packet, it just strips off the outer header from X and delivers the packet, source address A, destination address B, on the arrow that you see labeled 6 to the host. And that fundamental level of indirection is the basis of all of the LISP use cases. If host B decided to move somewhere to another site, that was attached with XTRZ, then the locator now becomes C. That's kind of an interesting concept. A can keep a connection with B no matter where B moves. If Jeff right now just changed to LTE, this connection would not go down because the open meeting connection is going to the EID Jeff, not to the IP address of his Wi-Fi router in his house. So basically, we're mapping these EIDs to locators or RLOCs.
Yes. Can I say something here?
Go ahead. Yeah.
Important
Important
thing here is think about like an MPLS. Any device between XTRX and XTRY, they are not aware of the host A and host B. So you will see that this will give us scalability for sure. So any device between X and Y, they just need to give the reachability between X and Y. That's it. Okay, their function, if it's on the internet, BGP routing system will resolve those reachability of the locators X and Y, and this gives scalability for the solution. Okay.
Absolutely, that's absolutely correct. And when we talk about MPLS being run in the core, or we're talking about LISP running on the edges, these are overlays, right? Which means the addresses that are part of the overlays are not known by the underlay. So the example here is these two clouds on the edge that are labeled EID space, they're on the overlay, and the underlay is where the RLOC space is. And so it's no different that if the RLOC space was running just regular IP routing or MPLS, or both. In other words, LISP can run over MPLS, right? Don't forget that router X is going to encapsulate a packet to Y. If there's a label switch router in between X and Y, it's going to be an overlay over an overlay, so to speak. Okay, but we don't require it. Okay.
Okay.
Now, what's also interesting is what if host A has an IPv6 address and host B has an IPv6 address, and we call them IPv6 EIDs? Well, what you can do now is you can establish a TCP connection with IPv6 addresses between the two, and the RLOC space core doesn't have to support IPv6, right? That's going to allow us to deploy IPv6 faster than otherwise, because today to get IPv6 deployed ubiquitously, every node along the path from A to B would have to support IPv6. Not just the routers, but the switches, the host operating systems, the firewalls, the load balancers. It goes on and on and on. But by having an overlay, you can do IPv6 over the top of an IPv4 underlay.
Sure.
Okay.
One of the
early days when Facebook was IPv4 only company, they actually used LISP to provide IPv6. It was one of the early IPv6 days, probably 5 or 6 years ago.
Okay, this is good because one of the questions which we will discuss about the IPv6 transition mechanisms and LISP use case for the IPv6 transition mechanism. I didn't know that Facebook used LISP as a v6 transition mechanism. Wow. Okay.
Yeah, this was in about the 2008-2009 timeframe, and people that had IPv6 on their operating systems, because it was, the host vendors implemented IPv6 in their kernels much faster and got it deployed much faster than the router vendors could get it deployed. Now that's kind of not fair. The router vendors had IPv6. It was a question of deploying all of that at the same time over a large internet, which is taking 20 years as we see, because deployment's really hard, right? A lot of gear has to change, a lot of coordination, tools have to change. So yeah, so it was an interesting exercise we did. And if you later want to talk about the details of that, I can get into the details.
I think let's
so
move
the
to
key
another
here is, go ahead.
I think let's
Say
move
again?
to another that 1 billion registration slide as well. I want to see that. Some scalability numbers.
Right, okay. Yeah, so to talk about the 1 billion slides, we first have to talk about the mapping system, and that's the top part of this. So for the IPv6 EID for B, for encapsulators to encapsulate to Y to get packets to B, you have to have a mapping system. In other words, you have to map EIDs to R logs. So what happens is this XTRY would then register to a map server, and we'll talk about the mapping system as a whole, but there's map servers and map resolvers, and you could very much think of them like the DNS system. What the map server does is store these mappings where B maps to this RLOC list of Y and A maps to X. Now note, there can be many RLOCs in the RLOC list, and you can load split packets across them. And if you need to load split packets, you don't have to tell the routing system underneath that anything has changed. This is absolutely crucial to scale mobility. A and B could be moving around the whole time, but X and Y are IP addresses of routers that are attached, are bolted into racks that are part of the BGP system that don't have to change. So we really have created a very scalable mobility system without the BGP core having to know what's going on. And we can explain that later.
Okay.
But the idea is the mapping system receives these registrations and keeps them alive. And as EIDs move around, they can change the RLOC set. And as encapsulators like X are encapsulating to say Y and Y prime, they can actually test using underlay telemetry between X and Y to see is Y better than Y prime? And if so, you can switch paths by simply encapsulating to a different RLOC at X. Nothing has to change in the routing system in the underlay. This has huge scalability benefits as well. So what happens is when a packet, we'll go just through it quickly and then we'll get directly to the questions. When a packet from host A is sent at time 1, if XTRX doesn't know where B is, in other words, there's no routing table entry in X for B, it will then at time 2 send a map request for B. And that's sent to a configured set of map resolvers that X knows about. And the map resolver will know where in this mapping system that B is registered. And so the map request then is forwarded at time 3 to the map server that has the registration. Then what happens is the map server could either proxy reply, which in this case is showing you at time 4, telling X that since you made the request for B, I have an authenticated and authoritative mapping for B. Here it is, it's Y, and gives it back to X. X then caches it, and then subsequent packets then just encapsulate to Y and Y prime if there was 2 RLOCs. Now, if the mapping from B to Y changes to say Z and Z prime, there's an event notification that goes back from the map server to XTRX, so it knows that the RLOC set has changed. So now it can encapsulate to the new location where B is. This is a pub sub feature of the mapping system. Okay. Now there's another option where when the map request goes to the map server knows Y and perhaps Y prime are RLOCs for B. It can forward the map request to Y and Y prime. And Y and Y prime could decide what's the RLOC sets it map replies back to X. Maybe if X is in the US and Y is in the US and Y prime is in Europe, we don't want to tell X to encapsulate to Y prime. We want to tell X just encapsulate to the closest entry point to the site, which is on the US side. So there's a lot of policy that can be done on a per source basis. The internet doesn't support S, D routing. It basically routes destination based only. But if my packets to Jeff, let's say my packets to Jeff would go one way and somebody else that's in San Jose wants packets to Jeff to go a different way, we could spread load out. We can't do that with the underlay today, but we can do that with an overlay.
Can I say something here now? S, D routing. which is very cool terminology. So those who knows multicast S, G entries, huh? So SSM, FIM SSM, and of course multicast GRU. So S, D routing mean what? Source and the destination. So it's basically IP is destination based lookup, but not source and destination as a pair. What LISP can do, he's explaining here. Just I wanted to highlight that. And nice terminology, by the way. Thanks for that.
Yes. Yes, that's exactly right.
What's important to understand, you don't need to do S, D lookup everywhere. You just do it on an enforcement point, and this is how you scale.
Right.
All the it's in control plane.
Yeah, Jeff makes a good point. If you did S, D, everybody would have to have a route for S, D. And let's look at what S and D are. Are they S/32 and D/32? Are they two host routes, which would blow up the routing system, because then it would be a flow cache essentially in every single router. Clearly that won't scale. Could we make it work where it's S, or S/prefix, D prefix, which means all packets from San Jose to Chicago would flow one path. The packets from San Jose to Houston would flow a different path, because the prefix for the source would be San Jose, and of course the destination prefix would be Chicago and different. That would scale a little bit better, but then you have these aggregate flows. We do that today with BGP and policy, but it's still destination based, right?
Yeah, actually, because even in the multicast, whenever you push those S entry into the control plane, not just wildcard like ASM, any source, you put more entry, so it's bad for scalability, but good for some traffic engineering and optimal routing. Same thing here we are talking about.
Yeah, that's true. And the unfortunate thing is we had to put S, G into multicast because we had to send packets in a loop-free manner. So we cared about where packets came from, and therefore you had to put the state in the routing system for that. It would be nice if we didn't, but then we would have hotspots, which is called a star, G tree, and we know how that all worked out, right? So
let's move on. Another slide.
Do you want to go to the questions, or let me look at the questions?
So yeah, I can read the questions and we can start from there. I can read them.
Okay, go ahead.
Okay, first question: what are the most common use cases of LISP? Which one do you see in the real deployments?
Okay, so originally we used LISP to solve the multi-homing site problem, as you see in this slide right here. And on that, we were able to build VPNs on top of that. So a site would be able to have two routers. This would be like, say, a branch bank office or something would have two routers to do two different ISPs. And it wanted to control which ways packets came in for all the hosts that were at its LISP site. And so because it had two RLOCs that would map to the prefix of the entire site, it would only be one mapping system entry in the mapping system. So that was nice, and it scaled really well. And then we could load split traffic. Now, if you wanted to be able to support VPNs, we would just have this thing called an instance ID that was prepended to the EID that said that this was the more specific, or the IID, EID was a two-tuple. And so we can use different RLOCs and come in for different VPNs, and we could have these closed user groups. And that works very nicely today for multi-tenancy. So that was the very first use case.
For that point, can I ask a question? For the VPN ID you set, I think it's equivalent of RD in the MPLS, route distinguisher, or pet identifier in BGP ETPET, right? Am I right?
Oh, very good question. The instance ID is basically a value that's put in the LISP header, and the underlay knows nothing about it. So the mapping system would know 1, Jeff and 2, Jeff. What that means is Jeff has registered to the mapping system with in instance ID 1 and instance ID 2 with the same EID Jeff, and that the locator for both of those is his home Wi-Fi. And so maybe you are talking to him on 1, Jeff, and I'm talking to him on 2, Jeff, and you and I can't talk to each other. So rather than having all these import-export rules on making VPNs work like AT&T and Verizon did over the years, and BT, all the European guys did, we don't have to have that. The basic mapping system, which is completely out of the data plane and out of the routers, do that mapping. And then you just qualify it with this instance ID that creates a 2-tuple in the lookup.
Okay.
Makes sense?
Yeah. Other use cases, let's talk
Okay.
about them.
Yeah, so that's the VPN and multi-homing was the first use case. Of course, what motivated LISP or locator ID separation in the early days of 2006 and 2007 was, is there a way we can keep routes out of the routing table, and that all these edge addresses don't have to go in to the core, because we want to put prefixes in there and get aggregatability. And so by just using the attachment points, I mean, if you look at host B's site right here, there's lots of IP addresses that you wouldn't want to inject in the core routing system as /32s or IPv6/128s. So you would put them in prefixes, and then you would have prefixes put in the mapping system. But the underlay would only know about Y. And it turns out Y's IP address would come out of the service provider connected to. So those were provider assigned addresses. Y would be an AT&T address. And if Y prime had a connection to Verizon, Y prime's IP address would be Verizon's IP address. But the IP addresses in this LISP site where host B is could come out of any address space, and typically would come out of provider independent space. That means people now could have their own IP addresses and move from service provider to service provider, or in today's internet, move wherever they want, from Wi-Fi to Starbucks to Pete's or whatever, and keep the same IP address. Could you imagine keeping the same IP address and keeping a DNS name that never has to change? The DNS to IP address, or EID, would never have to change. Jeff.com, I could reach him no matter where he's roaming all the time, because he always maps to an EID that never changes. What changes is his binding to where he's currently located on the network. That level of indirection is so powerful. Okay, so that creates mobility considerations. So the first mobility thing we did at Cisco was VM mobility in a data center. We'd use vMotion to have an IP address move from one server to another, and you didn't need a layer 2 network to connect it together. It was all layer 3 directly into the server. The top of rack switch, i.e. router, and end of row router, they were all routers, and you can then move these IP addresses around without injecting them to the underlying routing system. Because what was changing? Host B was changing from Y to Y prime, and that was being registered to the mapping system. So a top of rack switch called X that had to encapsulate a packet from A to B would now encapsulate to Y prime or Z or whatever. So you see, but go ahead. So VM mobility was one of the early use cases, and now we're using it on cell phones and aircraft.
Definitely.
And it all is based on the fundamental idea.
So
that's a very important point to add. Sorry.
Go ahead.
Someone kind of worked with VMware. vMotion till really late required layer 2 connectivity to provide hitless vMotion. So which would lead to deployment of stretch layer 2 across sites, across the globe really, right? Because if you wanted to move VM from one DC to another. So being able to do it at layer 3 in early days was a huge thing.
Yeah, also
I would always tell VMware, I go, don't tell people that they need to stretch L2 to get vMotion to work. And they say, well, the only way to get it to work is to be on the same subnet. And the answer was, no, you don't have to be on the same net. VMware, your requirement is that the IP address doesn't change. How the networking people make that happen doesn't have to stretch a subnet and do layer 2 all the way across.
Definitely good point. But my question here, still we are in the same question, but sub-question in this question. Let's say without Lisp, Jeff, actually this question I would ask to you. Let's say without Lisp, if I would want to do with BGP and I want to advertise into the routing control plane /32s with BGP, is there an automatic way of doing this?
You can advertise into BGP whatever you like.
Automatically.
But it happen on the boundaries. Most people wouldn't allow anything logged on the /24. So you won't get global reachability.
No. I am asking for the data center use case. Let's say two data center, VM moved from one data center to another. Of course, with Lisp, it is automatically done. So the ITR XTR node will inform the mapping system that /32 moved to this data center. Lisp is doing automatically this one. Can we do this with just BGP automatically?
It's a problem because you would like to aggregate, right? You don't want to see host routes anywhere.
Definitely. In the control plane, in the BGP control plane, even BGP can scale. I don't want to see. I am okay. But is there a way to do that automatically?
So let me answer that. I can answer the question.
Please.
So it's not a question of BGP can do it. BGP can inject /32 routes. The question is, if you want to do it, is a separate question, and that's what Jeff's saying. It won't scale. I've known many enterprise sites, especially the brokerage firms, that did do /32 routing in their data center, and they scoped it so the scale could be kept under control. They didn't do it with BGP, but it would work with BGP. They did it with IGPs. Okay, it's discovering that something has popped up. That's the key. It's called source discovery. So if B moved all the way over where A was, and that XTRX was a LISP box, an OSPF box, or BGP box, and wanted to dynamically determine this B/32 now is in my site, and that since I discover it and it's still there, and it has to keep staying there because I have to know when to withdraw it, then you can take that /32 and using all three mechanisms, inject it wherever you want to do it. We'll leave Jeff's point aside for a minute. Do you want to do that? And he's clearly correct that on a larger scale of any sort of mobility boundary, you have to be careful because /32s are flowing everywhere. That's why mobility was hard to do using just the regular routing system. So what we did with
describe map mobility as done today in a VPN because it's kind of close to what people do today. So when VM moves and you use any kind of gateways, your IP address and MAC address don't need to change. You're still on stretch layer 2. You're using ability of BGP to detect there is new MAC address or new location MAC address is bound to and advertise this route. However, it's control plane driven, and it will take second 2 or 3 propagate new MAC address locator to the rest of the fabric. So there's similar mechanism done with the VPN, but you need to be aware of amount of time it takes, and it's definitely not hitless.
You are talking EVPN type 5?
I mean
you are talking EVPN.
Well as EVPN.
VM moves, you'll advertise new MAC address that is attached to another leaf, right?
Yeah, but that 2-3 second, even with Lisp, I think we will see that delay, right? For the new locator to advertise.
In the VPN case, absolutely, yes.
Okay, so there's some differences here. There's a lot of good points being made. He said you'd have to inject the MAC address. That doesn't sound like layer 3 routing.
Yeah.
You know, it's layer 2. So it's BGP being used as an underlay to support a layer 2 overlay on top of that.
Absolutely.
Right?
Yeah.
That's what's going on here. Lisp doesn't do that. I mean, Lisp can support layer 2 overlays, but we don't want to encourage it because there's so many better ways of doing it. But the key is that BGP provides any-to-any routing, which is really good. And when this host B moves around, BGP's job is to send the /32 to every BGP router that's part of some mobility domain. But maybe not everybody wants to talk to B, but you have to use the resources and the time for route propagation to get everywhere before anybody could talk to B in its new location. This is a huge convergence problem. Obviously won't scale. You're using resources that you don't need to use.
Could we use,
so the fact that,
maybe for this point, not sending everyone, but whoever just need it, maybe we could use RTC, route target constraint type of things, maybe?
No, so you don't really need constraint because only devices that participate in the same VPN will import the route, right?
Yes,
but
still they will receive.
Still
they will receive. They will not import, but they will receive. But for us to prevent source to not to send at all, so we need this kind of maybe RTC.
So Dina is going to explain how this does it really more intelligent way rather than flooding to everybody.
Yes, let's hear.
So the point that you were making about, well, you said something that BGP only has to send it to the nodes in the VPN. Well, that helps scale the problem down, but VPNs can also be very large, and that still may not be scalable. But the fact that it's not, capital I internet is like a non-starter. I would argue that sending it to all everybody in the VPN is a non-starter as well, because some VPNs are 10,000 sites now, if not getting larger. So that's pretty large. That's moving traffic topologically over the speed of light, geographically to many places, and you're not going to get your good convergence. So the idea is when host B actually moves to that site, all it has to do is tell its map server, only the map server, because it's the one that's holding the registration that says B maps to Y. What host B wants to do is when it moves, it only has to send a single message to the map server. Now, there could be a pair of map servers there that are topologically distant, so there's redundancy and fault isolation and fault recovery. So that would mean, host B would send 2 LISP map register messages to map server 1 and map server 2. We'll show you that on the other slide when we get to it. But the fact that everybody that sends map requests to the mapping system knows to come to this map server, whenever map requests come to that map server, they're always given the latest information. And the information is authoritative and authenticated in those 2 places. So if a new map request came from host A prime that was somewhere else going to B, it would find its way to this map server, and what would be returned was B maps to X now, since we said B moved over to X. Now, another point was made by you is saying, why don't we just remember everybody who cares about B and let them know? That's a huge scaling problem. We have 2 cases in the internet today where we don't do that for obvious reasons, right? When I go to a web page and click on a link, and you wrote that web page, Jeff, and you decide you want to change that link to somewhere else, do you tell everybody who now has that page cached that now the contents of the page has changed? No, because Jeff or the web server didn't keep track and shouldn't keep track of everybody who has accessed that page, because that's a huge number of entries you'd have to keep. This is fundamentally what PubSub does. It remembers who's interested, who subscribes to something, right? So another example is DNS. We know that we don't get, if Jeff.com changes and there's new A records, the only way I know it is that I later request it, right? And when I request it, I get the up-to-date information. But that stuff could have changed yesterday. And I don't have the most up-to-date stuff. Now, if I'm not talking to Jeff for a couple of days, then it's no problem. And maybe my cache time's out. And then when I want to talk to Jeff, I get his new location. DNS doesn't support. We support DNS updates, but that is just an automatic way for Jeff to change his A record for Jeff.com to the DNS system. But it doesn't inform everybody who's ever did a lookup on Jeff.com that they may be interested.
Actually,
this is a huge scaling problem to make this work.
Okay. Very important point. Very important point, and we have a terminology for this. Maybe you are using as well. Push and pull-based control planes. So routing system, even with BGP, as you said, even using the constraint like route target constraint, etc., still we are pushing every site in that VPN, pushing, routing, BGP, IGPs. But the LISP is pull-based, so whenever you need some information to reach, or some place to reach, or whenever you need to cache, you just, whenever you do, you pull from the authoritative server, which is MRMS. This is definitely a scalability we are talking about. And nobody could argue about the scalability of the solution anyway, and definitely good point. Push-based versus pull-based control planes. Yeah.
And segmentation and ability to segment different databases as per instance, right?
Yeah.
You cannot pull every BGP route because it's internet global system. In LISP, however, you can segment it, so you create limited domains. That's scale.
Right. All good, all really good points. Okay, so let's look at, the deployments we see, So there's the old-fashioned deployments, which is VPNs, multi-homing, VM mobility. We do see some test deployments by putting LISP on a mobile phone. Now, there's an important point in terms of mobility to talk about. When we talk about EIDs and RLOCs, in this diagram here, you see that they're not co-located. But with the advent of virtualization and containers and microservices, we see services pop up and down and functions and stuff. We see these things pop up and down everywhere in the network. And they're either cloud-based or colo-based or bare metal-based. And so what happens is when B pops up anywhere as a container, its RLOC is where it is at the moment. So maybe if it pops up, a container pops up in a VM on AWS, then the RLOC for it is AWS's Ethernet 0 interface. But that thing could shut down and then pop up in GCP. This is making LISP work really well. But it turns out that the thing that's coming and going has the RLOC and EID co-located. Okay, so here they're not co-located, but in LISP Mobile Node, for instance, LISP Mobile Node is an implementation of LISP that goes on a cell phone, where the radios, the IP addresses that are received on the radio links are the RLOCs, and the EID is like a loopback interface that's used for all transport connections. Obviously, when that phone is moving around, the EID stays the same, but the RLOCs change, right? Because if you roam to Starbucks, the Wi-Fi IP address will change. You roam back into your house, the Wi-Fi address will change. The LTE address will stay pretty much the same because it's being home to AT&T and Verizon, and they have huge, large subnet footprints where maybe the IP address doesn't change. But if you're on a high-speed train in Europe and you're going between lots of different cellular providers, you may change from Vodafone to BT, and your IP address will definitely change. So we don't want this to affect transport connections, right? So what happens is all the transport connections are based on the EIDs. And I have a couple demos that I could forward to the group that I've been doing things on iPhone, iOS by doing multicast and unicast by showing you how the phone could roam and keep connections up as the RLOCs are changing underneath. Very interesting.
Actually, Dino,
in the advent of, go ahead.
Very important question at this moment. So you gave the phone example. And to be honest, why even I didn't put here in the questions. So mobile IP, right? Mobile IP, so has been around for also decades. And how mobile IP wouldn't solve this issue? And I mean, if you would compare LISP and the mobile IP solution, what would be the advantage of LISP? What mobile IP cannot solve? Is there anything?
Well, mobile IP is based on anchor points and has a lot of messaging, and it requires handshaking by 3 or 4 different locations, and all that handshaking causes you to drop packets, and it's not a seamless experience, right? So what LISP does, it monitors data flows. So when that mobile phone is moving around, it knows what EIDs it's talking to. It's in its cache, right? Because it has to encapsulate packets to the RLOCs. So what it does is it makes sure that it notifies only the top 10 talkers that it's talking to at the moment. So they know the new RLOC that I'm going to be at in a minute, right? So what if I know I'm moving or I'm on a boundary, I will not only tell the mapping system where my new RLOCs are, because don't forget there's going to be new sources that are going to want to talk to me. But if I'm talking to you two guys, I'm going to go ahead and send map notify messages to you to tell you to do a lookup, or actually, when I send you map notify messages, the actual mapping is in the message. So I don't have to say, Jeff, go do a lookup. What does that mean? What it means is I tell Jeff with a message that can be lost and may have to be retransmitted to go do a new lookup into a database. He sends a message to that database, which can be lost or retransmitted, and then a reply comes back. All that has to happen before he starts encapsulating my new location. What happens in the middle of that? Packets get dropped on the floor. We want to be able to have near zero packet loss. So with messaging, you have the speed of light drop. So you have to tell people and set the expectation that packets will be dropped, because once you're talking to somebody and it decides to move independently and asynchronously from anything else, your packets are still going to go to that old place. And yes, the old place if it's a router, like Y, can maybe then forward it to the new place. But if the thing that's moving is also the RLOC, you're going to be sending packets to where it no longer is. And the packets are just going to be dropped on the floor. So what you want to do is the speed of light problem is going to happen with all messaging protocols. And LISP with its control plane has the problem, and so does mobile IP. What we did in LISP to have near zero packet loss was we did these things called predictive RLOCs. Okay? Guess what? I'm talking to Jeff, and he's on a high-speed train in Holland. He's going southbound. Okay? I know that wherever he goes, that he's going to hit these roadside units. These roadside units are devices that are connected to the underlay that have IP addresses that don't change. They're part of infrastructure. And Jeff's going to pass by A, then B, then C. Well, what Jeff's going to do is he's going to register the mapping system is that I'm Jeff, and I have a predictive RLOC set of ABC, okay? And once he's at A, I know to send the packets to him. When he arrives at B, I'm going to send packets to B, and then when he arrives at C, I'll send packets to C. Now, how do I know where he is, and then I'm not sending packets to A when he's sitting at B, right? Very easily. I'm going to send him to all three places. And when Jeff leaves A and appears to B, packets will already be coming to Jeff because I encapsulate him to B. Now, when Jeff wants to talk back to me, and he has LISP encapsulate with a source address of B, I could know because he registered RLOCs A, B, and C as in a sequence. I know Jeff's no longer at A. Now I can just encapsulate to B and C. So the fact that we have to send it to the entire RLOC set sounds like we're wasting bandwidth. But I know where he no longer is, and I can prune the set of LISP.
Exactly. But in your example,
now,
Jeff is EID, right? In your example?
Jeff's the EID.
Okay.
Jeff's the EID, and the RLOCs are A, B, and C.
Uh-huh.
Now what happens is I'm sending packets to B and C. Jeff's still traveling southbound.
It's like
he gets to C.
Dino.
I'm sending packets to B and C. He hasn't sent the packet yet. So yes, I'm unnecessarily sending packets to B. But once he sends a packet to me, then I know he's only at C. Guess what I do next? Now I send packets to A, B, and C again because he may go back. Or A, B, C, D may be a circle. Or A and B may be two towers where he's going in and out of two towers because of the cellular network. So I don't want him to signal when all this is happening because it just takes too long. So I'm actually using this unicast EID as kind of a multicast replication sync point.
Definitely, because
and that's what
I would say that you are doing almost like live multicast. You are sending to all those.
A great comparison.
Yeah.
That's exactly what we're doing. Yep. We're set. And with live, you want to send it on different paths, right? Well, if Jeff could have two RLOC sets, not only ABC, but he can have XYZ. XYZ could be the cellular network that he's going across those three cells. And ABC are the roadside units that are on Wi-Fi. And yes, me as an encapsulator could say, I want to encapsulate to X and A because those are the Wi-Fi access point and the cellular together. I may want to load split traffic between X and A, but it seems like A is getting a lot of loss because I'm RLOC probing. Me as an encapsulator, I'm RLOC probing A. And A's getting kind of a loss. Well, I'll use cellular now. But now when he moves to Y and B, maybe Y is not that good, and I can now send to B. LISP can do all these kinds of things, and it's done at the edges where the underlying routing system and all the organizations that connect RLOCs together don't have to be involved in this. It's quite powerful that you can do this at the edge and at the user device.
What I see here, the trade-off between the convergence time versus maybe bandwidth usage, right?
Yes, okay. That's the trade-off. Absolutely.
Okay.
You got it.
By the way, I want to say thanks to Jeff because I can talk to Dino like 5 hours. It's very interesting and I'm learning a lot. So predictive RLOC. Wow. This is another thing.
We have an RFC for it. It's a working group document in the IETF. And I'm one of the authors with 2 Huawei folks that are doing it because they wanted to solve a mobility problem. So please have a look at it. It's pretty short RFC.
Sure.
So or internet draft.
Definitely, I will do. So next question. Okay. So I think we talked about this one, but since I will share these videos also individually, not just as a single large video, so let's talk about this point again. What does LISP control plane and LISP data plane means? In some technologies, like EIGRP over the top, they used also LISP. Was it LISP control plane, LISP data plane? I mean, you don't have to, of course, talk individual technology, but when we hear LISP, this solution is using LISP control plane, not data plane, or vice versa, what it means?
Yeah, that's a really good question, because a lot of products are like Cisco's SDA uses LISP as a control plane, but uses VXLAN as the data plane. And so what people are, when they say they use the LISP control plane, what they mean is they're using the LISP mapping system. And what the LISP mapping system is, a database system that allows you to map key value pairs. And it's done at the network layer. The network layer has a database now with IP addresses in it. It could be names, it could be geo coordinates. There can be these predictive RLOCs. We can be replication lists. These are all the things that the value that's returned when you do an EID lookup. So it's a general key value store that's distributed like DNS, but it's updated much more dynamically than DNS, and it supports pub sub. So if you want to send, if you set this S bit in the map request, if I send a map request for the EID Jeff and I set the subscribe bit, it means the map server that has Jeff registered to Y will then inform me if Y has changed to Y prime. So I get a notification back from the mapping system that Jeff has changed. So this means that this database system also can support pub sub on a pretty large scale. We're really trying to see how this can work and how it can scale. Because when we talk about Cassandra, or we talk about oh, I forgot the name. What's the information bus that are being used a lot by a lot of people? I'm drawing a blank. Jeff, you know what I'm talking about. That has pub sub capabilities, a regular database.
Protobuf, no?
Protobuf, no.
XCD, Zookeeper.
Yeah, they're all of the same elk. Yeah.
Someone says
I forgot
Kafka.
the name of it.
Someone says
that supports pub sub. Yeah.
Kafka.
But anyways, I just drawing a blank on what it is. So when people say they're using LISP control plane, that means they're using the mapping system. And since LISP can support multiple data planes, which means if Y can register and say, I could only support encapsulations, MPLS and VXLAN, and maybe Z will say, I only could support L2 TP and
or just
GRE or
just plain
like
IP maybe.
Or just plain IP, yeah, right. IP and IP, right? Or LISP, and you know what? EIDs can come in lots of forms. They can be a geo prefix, they can be a MAC address, they can be a V4 address, a V6 address, a distinguished name. All these different things could be registered to the mapping system. And so you can actually, X and Y could actually be geo coordinates. So if Jeff, the EID Jeff, registers to the mapping system with his GPS coordinates, he's not only telling me what the IP address is, but he's actually telling me his physical location. So we have applications that are running where there was one application that we had where we wanted somebody's in their car and they're on their cell phone and they're going 50 miles an hour. This sounds like a dangerous situation. So what we want to do is we want to shut off his cell phone. So we used LISP in that case to show that this guy was registering his GPS coordinates at different times. We would timestamp them and see that the GPS coordinates changed, and we were able to compute distance and speed. And when we found that the speed was over a configured value, we would shut his phone down. So he would get frustrated and put it down and drive safely.
Wow, this is nice.
Things like that we were able to do.
This is cool, and you are supporting through your company lispers.net this kind of applications as well, right? Consultancy you are giving.
All these use cases I'm talking about and these different EID types and RLOCs are all supported in the lispers.net system. You could go look at the code on GitHub. There's pointers on my website where you can go look at it. And please, if anybody that looks at it and has questions and wants better understanding, just drop me an email. So it's no problem at all. It's to aid in understanding and trying to forward the technology, obviously.
Definitely.
So that's what they mean. Yeah. And the thing is it's not critical that LISP data plane is used. I mean, there are some features that the LISP data plane gives you that others don't, and that's one of the questions that you had that I was going to use as an answer to the get VPN question. But we're not quite there yet. So when we get there,
okay. So if
know,
I would summarize, if I would say that, would it be correct? Very high level. If I am using mapping system, then I am talking about control plane. But if I am using the encap of LISP, encapsulation, decapsulation, then I am talking about the data plane.
That's absolutely correct.
Excellent. So let's move on to a new question. Can you talk about LISP role in Cisco's SD-Access? Nowadays, SD-Access is very, very popular, Cisco SD-Access, and people want to know what's the role. Little bit we talked about, but now as a separate question, separate discussion topic, let's do this.
Okay, so SDA is an overlay technology that Cisco has put in a lot of their products, both hardware and operating systems, to support overlays on the campus. They support layer 2 overlays and layer 3 overlays, so nodes on a campus could move around freely, attach to printers, and talk to each other. So it's basically the mobility function of LISP is what they're implementing in these products. They're also attaching IoT devices to this infrastructure as well. So these IoT devices act as EIDs, and the routers that attach to them are used as the RLOCs. So in this case, the mobility is the RLOC and the EID are not co-located because they don't want any host to change. This is a network solution, so the RLOCs are in Cisco devices, and the IP addresses of the devices are the EIDs, just like you see in this picture here, where A is the EID, and a Cisco device is X, the RLOC. And so what they're doing there is they decided to use VXLAN as the data plane because they have a layer 2 overlay and a layer 3 overlay. They could have used LISP and put MAC addresses in LISP as well at the data plane, but VXLAN was well suited for layer 2 overlays and layer 2 encapsulation. And there's a lot of chip vendors that support VXLAN. And Cisco themselves put VXLAN into hardware. So VXLAN is used as the data plane of choice to do both L2 and L3. Probably a good choice, but when you talk about VXLAN encapsulation versus LISP, it's just another UDP encapsulation with a different port number, and the VXLAN header and the LISP header are identical. And the VXLAN header was based on the LISP header, but just didn't use all the flag bits because didn't want to implement all those features. It only uses the instance ID flag to support VPNs or VLANs in the layer 2 case. So VXLAN is the data plane, and Cisco decided that all the policy-based management and access control would be use SGTs or TrustSec, but they needed a way to do the routing, and they didn't want to inject this mobility stuff into the underlying routing system in their IGPs, or we would have the problem we previously talked about having /32s everywhere. And of course, multiple campuses connecting together, this would be a large mobility domain. They didn't want anybody to take a system in one building and drive over to the other building, so it was a larger topology. So clearly /32s wouldn't work. So here they use the LISP mapping system to map IPv4 and IPv6 EIDs to RLOCs of these Cisco Edge devices, as well as MAC addresses as EIDs to IPv4, IPv6 RLOCs. So they support all that so when people say SDA, they say 3 pieces of technology are being married together. VXLAN as the data plane, LISP as the control plane using the mapping system, and TrustSec, the SGT, as the policy-based.
That's right.
That's it in a nutshell.
That's true, and it will be excellent answer. So what I understood is we are using control plane of LISP in SDA, data plane as VXLAN, and both layer 2 and layer 3 payloads are carried in VXLAN header. And of course, for the policy, we have also SGTs. Excellent answer. Thanks for that. And let's move on to new question. Okay, question 4 we are discussing. We talked just about Lisp role in SDA, and now vendor interoperability. Is there vendor interoperability? Can I use Lisp with Cisco and other vendors in the same network, for example, like Juniper, Huawei, whatever? Or is it just a software implementation we can see Lisp?
Yeah, good question. So in the early days, we did have other vendors involved. HP on their ProCurve switches supported Lisp, and they did show some interoperability. The Lisp implementation obviously is interoperable between Cisco, even though it sounds like one vendor. It was actually 3 different implementations because of the 3 separate operating systems, and it was supported in a lot of hardware, and the forwarding was done in a lot of in ASICs. Both those implementations did operate with my Lispers.net implementation, which is only a software-based router that switches packet software, as well as all the other. There was Lisp Mobile Node. I can't remember the old name of it, but the new name is called OOR, which is an open source implementation that support on WRT, Linux, Android, and iOS. And so those vendor implementations do support and interoperate with the open source public domain implementations as well. In 2014, when I left Cisco in 2012, in 2014, I got together with Arista, and we did a really interesting implementation with 5 different implementations. It was, I wish I could bring up the picture. And it's available on my website, so you'll be able to see it, is we put an Arista switch as a top of rack connected to a server, and we put an A10 load balancer connected to another server on the top of the picture. On the bottom, we put a ProCurve HP box that was a wired connection in a wiring closet, and then we used an Aruba access point, and then what we did is we had a Mac move from wire to wireless back and forth. It had an EID, and the RLOC was either the HP box or the Aruba box, okay? Just like you see here. And then at the same time, it was talking to an application that was running in the data center. And we saw that the VM was moving from Arista A10 back and forth. And those 4 data planes were interoperating each other using my Lispers.net as the control plane. I was the mapping system.
Can I see this one? Can I see this one on Lispers.net?
You can. Yes, you can.
I will definitely open it and I will check this.
Yeah. Do you want to say a word about FRR and Lisp?
Yeah, free range routing.
I think you'd be better equipped to say it, Jeff. Don't you think?
Yeah, so thanks to Dino. As you know, FRR free-range routing is an open source routing step that has the roots in Quagga. Dino decided to contribute his code to FRR, so there is truly open source implementation, and going forward, there's going to be proper integration of Dino's code into FRR.
And also let me add something about that. FRR supporting Lisp and supporting many other protocols as well, IGP, BGP, MPLS, etc. So it's worth to look at that, guys. When you hear FRR, it's just not fast reroute, but yeah, it's not. But we are talking free range routing.
And one other thing, the Lispers.net implementation has also been contributed to the Linux Foundation EVE project, the Edge Virtualization project. So a lot of the IoT work that's going on there for edge computing is using overlays, and I open sourced Lisp in February 2019 to be part of that project as well. So just to let you know that.
Thanks for that. And let's move on. Another question, actually, this one is a huge discussion. I think one of those comments in one of our webinar with Jeff, the guy was saying about Lisp, this is important. Can Lisp replace BGP for the global routing table we are talking about? And many people talked about this use case in the past also. I've seen even some Cisco Live presentations, etc. And what do you think about this?
Yeah, it's a huge misconception. LISP never intended to replace BGP. LISP needs BGP because we need an underlay that's scalable, and the capital I internet that's going to route RLOCs in a scalable way is absolutely necessary. It was never the intention to replace BGP. What we wanted to do is we wanted to ease BGP's workload by not putting so many addresses that were non-aggregatable into BGP. So basically what we're saying is LISP works on provider-independent address space, and BGP works on provider-assigned address space. So BGP would scale much better because you wouldn't punch holes in prefixes as much because of multi-homing and mobility. So BGP is very much an important ingredient in the overlay model.
So just a second. Why you are saying BGP would be PA and LISP would be PI? I didn't get that point.
Okay. So today systems are connected to the internet, and if their routes are being injected into the internet, basically those tail circuits that go to sites, those IP addresses come out of prefixes that are owned by the service provider that link goes to, and they are, and that service provider injects it to other peers as a prefix. So what happens is that prefix is basically advertising tens of thousands, if not hundreds of thousands, of RLOCs with one prefix. That allows it to scale much better. And those addresses that are being assigned to that tail circuit come out of provider assigned space, which means if I have a link to AT&T, the IP address on my side of the link to AT&T comes out of AT&T's prefixes. That's really important because those prefixes don't have to be, you don't have to punch holes in them, which means you don't need more specifics to be injected in case it has to move. If you want to change any of the site's addresses behind it, if you look at like host A right here, if you wanted to move host A anywhere inside a national or multinational corporation, it wouldn't have to tell the routing system that now you move this host A from the US to Europe. That's a big problem in the internet today. So what happens is when host A moves, you readdress it to something else. If you're going to move 10,000 containers from US to Europe, they have to be readdressed. And that means they have to have new DNS entries that have to map to them. It's a very manual process and very cumbersome. Where with LISP, it would happen automatically and you wouldn't have to readdress any of the systems because the EIDs stay the same. We do this, this is what we want to do in the Olympics. We want to build a network of all the gear that we want to support the video distribution. And we want to put it in a C container. And when we move from Pyeongchang to Tokyo, only thing that changes are the connection points into it, which means the RLOCs for all that gear have to change from KT to NTT, and that's all that has to change. All the addressability of all the infrastructure inside is out of EID space. And you see what happens is when we moved the C container from Korea to Japan, when it was in Korea, we were using Korea RLOCs because the routing system has to route packets to Korea. When we moved the C container is a physical container that goes on a ship with a bunch of equipment that's shrink wrapped. Once it goes to Tokyo, then what happens is we use the RLOCs that are associated with NTT. NTT in Korea, their BGP backbones didn't have to change because they're already advertising those prefixes. And we're just getting a /32 out of that to be addressed on the container side, on the C container side. Make sense?
The interaction that we've been talking about this whole time, you don't need to change your EIDs, right? You only need to change RLOCs because interaction is provided by mapping server itself.
That's exactly right. Well said.
Okay.
So in other words, LISP doesn't replace BGP. It makes BGP work better, makes it more scalable, and that's the really point.
Yeah, and if you want to make even a stronger statement is LISP needs BGP or it won't work because we won't have an underlay. I mean, today, when I do my testing, I can launch 1,000 containers on my laptop, and they're all running LISP, and they all talk to each other. The underlay is the Docker bridge that makes them all on one subnet. I could bring these Docker containers up and down and the IP address of the container changes because Docker is going to assign them a new one. But I don't care because I'm running an overlay on top of it. In that case, I don't need BGP container on my laptop, the Docker container on Jeff's laptop, and it will seamlessly. He'll have a different RLOC, and it's bringing up a new point too. If I want to hold a TCP connection between my container on my laptop and Jeff's container, not only do I need to know what his RLOC is, I need to know what his translated RLOC is because he's double netting through Docker and his Wi-Fi at home are NATs. And so I need to know his global address, and he needs to know my global address. So NAT supports, LISP supports NAT traversal. So when we say this host A and B can move around, it could move around anywhere. And if we look at the newer applications that are running, like running blockchain applications over LISP, we want these blockchain applications to move around anywhere and be accessible. Remember, blockchain is a decentralized mentality, and we want anybody to be an XTR and move anywhere to be able to validate blocks and do transactions. How do we do this in a seamless way? Because the people that are running the blockchain are going to be users like you and me, and not tech guys, not networking guys, not database guys, not OS guys. They're just people that want to make money by validating transactions. And so to make decentralization work with mobility, there's no other way it can work without an overlay.
What I understood.
And an overlay that could support NAT traversal.
What I understood, let me just talk about, and if I am making anything wrong, please correct me. So what Dino says is, of course, LISP, even in the first place, was not intended to replace BGP. And LISP requires underlay routing. It can be BGP, it can be anything, but RLOC reachability. Okay, that underlay for the RLOC reachability. So far, so good. Now, what also Jeff says, LISP is not replacing BGP. It was not intended, but LISP helping BGP to scale even more. And I understand this point why Jeff is saying, because let's say we have 1 million hosts on site A and another million of hosts in site B. Underlay BGP routing might summarize those 1 million entry as just single slash, I don't know, 14, 13. Another site, another million with, again, single entry slash 13. Route BGP control plane, or default free zone for the global routing table, we call it, right, needs to know 2 entry. But what LISP is doing as an overlay is carrying those millions of hosts, site A to site B communication it provides. Is it, how was it as a summary point? Correct, right? What I am talking about.
It was very good summary.
Excellent. So,
yeah. So let me ask you a question. If one of those hosts in a /14 moves away from where the /14 is being originated, what happens?
Oh yeah.
It's an outlier. It's an outlier from the /14. And since you want to move packets to it, you have to take that 1/32 out of it. And the only way you take it out of it is by injecting the more specific in the for the network.
Definitely, it should, that /32 /32 should be in the overlay.
But if it's an EID,
at the moment, video is stuck, I think. Can you hear me? You know?
Yes.
Yeah, now I think video is fine as well. So I think scalability and replacing LISP is not the case. Replacing LISP, BGP with LISP is not the case. And you heard from the inventor of the protocol this. I think it will end this discussion anymore on the internet. So when people again write this, Jeff, we can say, okay, we did this discussion, go and check the YouTube channel, and the inventor of the LISP was not intended to replace BGP anyway, and we explained the reasons. What was that? What did you say?
Blame. It's his fault.
Check them out and have the same answer, and we'll talk about that separately.
So, by the way, at this moment, I think it's a good time to maybe stop here. And if you would guys agree, I would continue in a separate session because we have many other questions. Probably will take another 1 hour. And it's better maybe keep it here. And then for the many other questions. In fact, there was one question, maybe very short, we can answer that. The guy asked couple times in the chat window. Let's answer that one as well. And I have some questions also in the chat window. I see many questions. I will collect from those guys and my questions as well. We should do definitely second recording for this. But let's answer this one.
Sounds good.
If there are two MRMS, Jatila is asking, how both will synchronize with each other if there are two MRMS?
When there's more than one map server that you register to, it's the responsibility of who's registering the EID to send it to both. So there's no cross synchronization between the two map servers. It's the ETR that registers to both of them. That's how the map servers can remain with the same state, but don't have to have proactive synchronization. Now, the map resolver is just a method. That's where we should go to the 1 billion slide. We didn't get to that. Maybe that should be used as a separate topic, how the map resolver finds the map server, because we're assuming 1 billion registrations could come into maybe 1,000 separate map servers, pairs of map servers, and we have to connect those together so when map requests flow to the map resolvers, they know where the map servers are. So if you want to talk about that now, we can, but that's a long answer.
So I think we will move the 1 billion slide in discussion on scale into the next meeting.
Next one, okay.
Definitely.
So inevitably going to happen.
Because
okay, sounds good.
At least another hour of questions we have, maybe 2 hours even. So let's keep it here, almost 1.5 hours. We talked about many questions, and also in the beginning of this session, we explained, Dino explained us how this solution is scalable. There was very cool point. I will definitely check on lispers.net also this predictive RLOG settings, so live multicast. We talked many things actually. I enjoyed again, and I can talk with Dino and Jeff hours and hours, but you guys are not watching entire long videos. That's why we are keeping it short. Put your comments under the video. This will be on the YouTube channel, and like it. Don't forget to subscribe to the channel. What guys would you say as a last point before we close?
So please don't forget to cover all the questions asked now so we can move them to the next session and get answered. So people don't do it for nothing. Okay?
Excellent point. Dino, so it seems you promised us for the second session as well.
Yeah, no problem. Anytime. We could do it really soon so we can keep the continuity going. So
thanks
if you want to do it next week, we certainly can.
Thanks a lot. Yes, let's set up that, and I will inform the live audience as well as we will publish that one on the YouTube channel as well. Those who watched this video from the YouTube channel, we have Skype group, and you can join their network engineers. You can just find us on LinkedIn. All of us we are using, especially Jeff and me, we are very active there. LinkedIn, Orhan Ergun, Jeff Tantsura, Dino is there as well. Put your comments if you have questions under this video. Also lispers.net I will put into description, so you can check that website. We had couple use cases, interesting stuff there, like predictive RLOG. First time even I'm hearing, and I will check more and try to understand more. So if you have question, go and please ask in the YouTube, or when we share this recording in LinkedIn, you can also type there your question. And thanks for everyone joining, and see you in the next meeting.